September 16th, 1943. Over Bougainville, in the Solomon Islands, First Lieutenant Kenneth Walsh sat in the cramped cockpit of his F4U Corsair, the engine ticking and cooling after another mission. He opened his personal log and carefully noted his thoughts in a steady hand. "This new aircraft changes everything," he reflected. "Its speed and firepower give us an edge the Zero cannot match. What we lack now is accuracy in deflection shooting." Through the worn, scratched plexiglass canopy, Walsh had just returned from escorting Navy bombers. He had watched fellow pilots, some veterans, some newly arrived, struggle with the same brutal reality. Hitting a maneuvering enemy aircraft while both planes twisted through the sky at high speed was less a matter of training manuals and more a kind of dark art. Deflection shooting demanded that a pilot fire not at where an enemy was, but where that enemy would be in the future, measured in fractions of a second that felt like eternity in combat. A Corsair closing at roughly 400 miles per hour might be engaging a Japanese Zero pulling evasive turns at around 300 miles per hour. The bullets themselves left the 6 Browning M2.50 caliber guns at about 2,700 feet per second. But even at that speed, they needed time to reach their target. At 500 yards, that flight time approached half a second. In that brief interval, a Zero executing a standard rate turn could move nearly 200 feet through space. The pilot, already enduring high G-forces, constricted vision, and the constant threat of enemy fire, had to lead the target just the right amount, adjusting continuously as range, angle, and closure rate evolved moment by moment. It was, in effect, a physics problem solved inside a human brain under maximum stress, one that even gifted pilots often failed to work out in time. Walsh flew what was then one of the most advanced fighters in the American arsenal. The Vought F4U Corsair had entered combat in February 1943 and represented a new standard for marine aviation. Its Pratt & Whitney R2800 double Wasp engine produced over 2,000 horsepower, driving the big fighter past 400 miles per hour and making it the first American single-engine fighter to break that barrier in operational service. The Corsair's armament was equally formidable. 3 Browning M2 machine guns in each wing, 6 in total, spat streams of 50 caliber bullets at nearly 800 rounds per minute per gun. When those bullets struck, they tore aircraft apart, shredding control surfaces, igniting fuel tanks, and snapping spars. On paper, the Corsair was overwhelming. In practice, the problem was simple. Those bullets still had to hit. The standard Mark 8 reflector gun sight that sat in front of Corsair pilots in 1943 offered no help with the hardest part of aerial gunnery. It projected a glowing reticle onto a small glass plate, essentially a fixed aiming point showing where the guns were pointed at that instant. Nothing more. It did not care how fast the aircraft was turning, how quickly the enemy moved across the field of view, or how far away the target was. Everything beyond that small, glowing image was left to the pilot's judgment. He had to estimate the lead angle entirely from experience and intuition, how far ahead of the target to aim, and how long to keep squeezing the trigger as the aircraft bucked and shook. Talented pilots gradually developed an instinctive feel for this, but only after months of practice and repeated combat. Many never did. Their tracers streaked harmlessly behind the target, every missed burst representing ammunition that had been shipped thousands of miles across the Pacific, only to vanish into empty air. Kenneth Walsh, flying with Marine Fighting Squadron 124, VMF 124, was one of the rare pilots who managed to master this skill with a reflector sight alone. On May 13, 1943, he became the first Corsair ace, downing 3 Japanese fighters in a single day and bringing his total to 6 confirmed kills. He had learned, through repetition and a natural grasp of spatial motion, how to anticipate the enemy's path, how much to lead at varying ranges, and when to fire that brief, decisive burst. But Walsh knew that his success could not easily be replicated. The average Marine pilot arriving in the combat zone had perhaps 200 total flight hours, with only a fraction devoted to gunnery. Of those, perhaps 20 hours involved firing at towed targets that obediently flew in straight lines. These training targets behaved nothing like veteran Japanese pilots in nimble Zeros, who twisted, climbed, and rolled to spoil the attacker's aim. Combat reports from 1943 revealed a sobering pattern. Many pilots emptied their ammunition belts during engagements without scoring a single kill. Their bullets passed just behind their targets, their mental calculations lagging by tenths of a second that meant the difference between victory and survival on one hand and failure and death on the other. What Walsh and his fellow American pilots could not yet know was that on the other side of the world, British engineers had already found a solution to this fundamental problem. They had created a device that would take the most difficult aspect of air combat, the calculation of lead during a turning fight, and transfer that burden from the pilot's mind to a spinning set of gyroscopes and a mechanical computer. In 1941, Britain began fielding the Mk gyroscopic gunsight, often called the gyrosight, a revolutionary instrument that measured an aircraft's rate of turn, using gyroscopes, and used that data to calculate the correct deflection angle automatically. Gyroscopes resist changes in orientation. When an aircraft turns, the gyroscopes inside the sight try to remain pointed along their original axes, while the airframe rotates around them. By harnessing that resistance through gears, linkages, and carefully aligned mirrors, the sight could determine how quickly the aircraft was turning. From that rate of turn, the system derived the necessary lead angle for a given target range and speed. Instead of a fixed reticle, the gyroscopic sight moved the aiming mark ahead of the target by the correct amount, turning deflection shooting from an instinctive art into something much closer to a repeatable process. Royal Air Force pilots flying Spitfires with the Mk gyro sight reported dramatic improvements. Aviators who had once struggled to score hits with a reflector sight suddenly found that their first bursts were striking home. The sight did not change the fundamentals of air combat. Tactics, positioning, and situational awareness were still crucial, but it removed the complex mental geometry that had long separated aces from average pilots. The United States quickly recognized the potential of this technology. American officials arranged to copy and adapt the British design, assigning Sperry Gyroscope Company the task of producing domestically manufactured versions. The U.S. Army Air Forces designated their model the K-14. The Navy and Marine Corps adopted an equivalent system under the name Mark 18. With minor adjustments to suit American production methods and cockpit layouts, the core concept remained essentially identical to the British original. At Sperry's growing facility in Lake Success, New York, more than 20,000 workers would eventually be employed at peak output, building not only gyroscopic gun sights, but bomb sights, fire control systems, and navigation instruments. Within 12 months of Walsh's log entry over Bougainville, the Mark 18 gyroscopic gun sight would begin appearing in Corsair cockpits in the Pacific. When it did, it would quietly change the mathematics of air warfare. The Mark 18 gyroscopic gun sight that would eventually sit in front of Corsair pilots was physically larger and more complex than the simple Mark 8 reflector that it replaced. Where the Mark 8 was compact and relatively lightweight, roughly 5 pounds of glass and metal, the gyroscopic installation weighed closer to 12 pounds and required careful redesign of cockpit panels and wiring. Sperry engineers were unapologetic about the added bulk. Inside the metal housing spun 2 independent gyroscopes, one sensitive to pitch, the other to yaw, each rotating continuously once powered. These gyroscopes, carefully balanced and supported on fine bearings, were the core of the system. They measured the aircraft's motion in real time, capturing the subtle nuances of its turns. The Mark 18's layout reflected lessons the British had learned in combat over Europe. The sight presented 2 distinct aiming references to the pilot. On one side, a fixed crosshair indicated the true line of the guns, the bore axis of the aircraft. This gave the pilot a reference for straight-ahead firing, useful for non-maneuvering shots, or when the sight's gyroscopic elements were still stabilizing after violent maneuvers. On the other side, the pilot saw a dynamic, gyro-stabilized aiming mark, a central circle surrounded by 6 diamond-shaped pips. This moving reticle represented where the pilot should aim in order to hit a maneuvering target. As the aircraft turned and the pilot tracked an enemy, the gyroscopes fed their measurements through a series of gears and linkages to reposition that reticle ahead of the target. The sight's operation rested on a simple but powerful idea. If one knew the own aircraft's rate of turn, the range to the target, and the characteristics of the gun's ballistics, one could calculate how far ahead of the target the pilot should aim. The Mark 18 did that mechanically. The procedure for using the device was straightforward, but it compressed years of experience into a few physical motions. Before engaging, the pilot set the enemy aircraft's wingspan using a control on the sight itself. The system included standardized values for known Japanese types. The ubiquitous A6M0, for example, had a wingspan of about 36 feet in its common variants. With the wingspan selected, the pilot then used a twist grip built into the throttle lever to adjust the size of the sight's ranging pattern. By expanding or contracting the diamond-shaped reticle until it matched the apparent wingspan of the target as seen through the glass, the pilot effectively dialed in the range. Mechanically, this motion told the sight how far away the enemy aircraft was. The internal mechanisms then used that range to compensate for bullet drop and time of flight. Once wingspan and range were set, the gyroscopes took over. As the pilot maneuvered to track his target, the moving reticle shifted automatically to the correct lead point based on the aircraft's rate of turn and the inputted range. The pilot's task simplified dramatically. Keep the gyroscopic reticle on the target and press the trigger. The complicated geometry that had once lived entirely in his mind now resided in spinning rotors and precision gears. Production of the K-14 and Mark 18 began in earnest in the spring of 1944. The K-14 first flowed to the European theater, where P-51 Mustangs and P-47 Thunderbolts began receiving the new sight in the late summer of that year. For the Army Air Forces, these installations promised to improve the effectiveness of bomber escort operations over Germany and occupied Europe. The Navy and Marine Corps followed, scheduling F4U Corsairs and F6F Hellcats for Mark 18 retrofits during the late months of 1944 and into early 1945. Priority went to units earmarked for carrier operations, squadrons that would be thrust into some of the fiercest fighting of the Pacific War. Among the first Marine units to receive the Mark 18 were VMF-124 and VMF-219, the pioneering Corsair squadrons selected to operate from fleet carriers. At Naval Air Station Santa Barbara in late 1944, these squadrons trained intensely for their new role. There, mechanics installed Mark 18 sights into Corsair cockpits, while pilots learned to trust a device that promised to replace instinctive guesswork with mechanical prediction. The aircraft that would soon join USS Essex carried not only a powerful engine and 6 heavy machine guns, but a small mechanical computer poised to change how those guns were used. Around the same time, Lieutenant Robert McClure, flying with the reformed VMF-214, received his first Corsair equipped with a Mark 18 sight. McClure was no novice. He had already scored several victories with a traditional reflector sight. Yet he immediately recognized that the gyroscopic gun sight represented something qualitatively different. In a letter home, later preserved in Marine Corps archives, McClure wrote that the Mark 18 felt like the difference between skilled guesswork and mechanical certainty. Years of accumulated experience in deflection shooting seemed to be compressed into a few hours of training with the new system. What he had once learned through trial, error, and combat now appeared as a shifting, glowing reticle that did the complex thinking for him. Meanwhile, Japanese naval aviation intelligence began to notice troubling signs. In late 1944, reports from the front and recovered wreckage indicated that American fighters were equipped with unfamiliar sighting equipment. Analysis of damaged Corsairs and captured documents eventually confirmed their fears. The Americans were fielding gyroscopic gunsights that could automatically compute deflection. To Japanese tacticians, this discovery was deeply unsettling. Their pilots had long relied on superior maneuverability to offset the advantages of American aircraft in speed, durability, and firepower. By forcing American pilots into difficult deflection shots, they had exploited the inherent difficulty of firing from one moving platform at another. If the Americans now possessed a device that largely eliminated human error in this area, a vital pillar of Japanese tactics was under threat. They quickly realized that no amount of additional pilot training could match the precision of gyroscopes spinning thousands of times per minute. Human reflexes, no matter how honed, could not equal a machine that measured angular motion mechanically and translated it into an exact lead angle. The Japanese response, once the nature of the Mark 18 and its cousins became clear, was to modify tactics. Fighter units were instructed to avoid prolonged turning engagements with Corsairs and other American fighters suspected of carrying gyroscopic sights. The new doctrine emphasized high-speed, hit-and-run attacks from altitude. Single, slashing passes, followed by immediate extension to minimize the time spent inside the firing envelopes of American guns. It was a reluctant admission of a harsh reality. Maneuverability alone no longer guaranteed even a small measure of safety. Once a Mark 18-equipped pilot had enough time to set range and track a target, the odds of that target escaping unscathed dropped sharply. December 1944 marked a turning point for Marine Corps aviation at sea. VMF 124, under Major William Giese, became the first Marine fighter squadron to deploy on a fleet carrier when it joined USS Essex at Ulithi. Alongside them, VMF 213 embarked as well, placing 48 F4U Corsairs aboard the carrier. Both squadrons had been outfitted with Mark 18 gyroscopic gunsights, bringing the latest fire control technology to the heart of the Pacific War. In January 1945, the Essex Air Group sorted for operations against Formosa and the Philippines. Corsair pilots flew combat air patrols, escorted bomber formations, and conducted strike missions, finally using the F4U in the carrier-based role for which it had originally been intended. The Mark 18 sights in their cockpits quickly proved their worth. Combat reports from these early operations described an unmistakable pattern. Pilots who had previously expended long bursts of ammunition with mixed results were now scoring hits more often with their initial volleys. Engagements that once required multiple firing passes could sometimes be resolved in a single, well-placed burst. The difference was especially important in bomber escort missions. Corsair pilots tasked with protecting strike packages often had to maintain specific formation positions, limiting their ability to maneuver into classic 6 o'clock shots directly behind enemy fighters. With reflector sights, attacking from oblique angles made accurate deflection shooting even more challenging. The Mark 18 altered that equation. Pilots could now engage from higher deflection angles, relying on the gyroscopic computation to place the reticle at the correct lead point. Instead of circling and jockeying for the perfect firing position, they could fire effectively the first time an opportunity presented itself. What had been a compromise attack angle with a reflector sight became a viable solution with the Mark 18. In February 1945, the focus shifted to Iwo Jima. During the invasion, Marine Corsairs flew from escort carriers, providing constant combat air patrols over the fleet and supporting ground forces ashore. The airspace over the island and the surrounding seas became a dense, chaotic environment of fighters, bombers, anti-aircraft fire, and weather. For Corsair pilots equipped with Mark 18 sights, this environment was still dangerous, but slightly more manageable. When Japanese aircraft attempted to break through to attack ships or ground targets, the gyroscopic sight allowed defenders to engage quickly and accurately, even under less than ideal conditions. Pilots reported scoring hits at angles and ranges that would have been difficult to judge with a reflector sight alone. The benefit of the Mark 18 became especially apparent in fights where ammunition conservation mattered. With reflector sights, a pilot might pour most of his ammunition into a single tricky target, hoping that at least some rounds found their mark. With the gyroscopic sight, a well-trained pilot could use shorter, more precise bursts, often damaging or destroying an enemy aircraft with fewer rounds expended. In several engagements, pilots were able to effectively engage multiple targets in a single sortie, something that had been far less common earlier in the war. March 1945 brought both continued offensive operations and a sobering reminder of the vulnerability of carrier forces. VMF 214, embarked on USS Franklin, took part in strikes against Japanese airfields and installations near the home islands. On March 19th, while operating off Kyushu, Franklin was struck by a Japanese bomber. The resulting explosions and fires ripped through the ship. More than 700 men died in the catastrophe, among them 32 members of VMF 214. The squadron suffered grievous losses in both personnel and aircraft. Those who survived continued the fight after the damaged carrier limped to safety, but the event underscored the brutal nature of carrier warfare. A ship bristling with the latest aircraft, guns, and technology could still be brought to the edge of destruction by a single determined attacker who slipped through. Despite such tragedies, Marine Corsair squadrons carried on. The Mark 18s in their cockpits did not eliminate danger, but they helped ensure that when chances to intercept attackers arose, those chances were used as effectively as possible. In April 1945, Operation Iceberg, the invasion of Okinawa, began. This campaign would see the most intense concentration of kamikaze attacks of the war. Japanese forces committed thousands of aircraft in desperate attempts to shatter the American fleet and halt the invasion. Marine Corsairs, many of them equipped with Mark 18 sights, became critical components of the fleet's air defense. Kamikaze pilots, once committed to their attack, typically flew a predictable profile. Approach from altitude, dive toward the fleet, and drive straight into a ship. For defenders, this predictability turned into an advantage when combined with a gyroscopic sight. Corsair pilots could lock onto incoming attackers, quickly set range using the sight's ranging reticle, and then allow the gyroscopes to compute the proper deflection as they maneuvered to intercept. Many reported first-burst hits against kamikaze aircraft, something that had been much less common earlier in the war. Between April and June 1945, combat air patrol missions over and around Okinawa resulted in the destruction of hundreds of Japanese aircraft. Official records do not always distinguish between kills achieved with reflector sight-equipped aircraft and those using gyroscopic sights, but operational reports consistently noted that units with Mark 18 installations were showing improved effectiveness. Perhaps even more consequential than the improved statistics was the psychological impact on the enemy. Japanese pilots who survived encounters with Corsairs equipped with gyroscopic sights described a profound sense of helplessness. No matter how violently they maneuvered, they often found that American tracers curved into their flight path with uncanny accuracy. The traditional belief that skillful flying and aggressive maneuvering could throw off an attacker's aim no longer seemed reliable. Once an American pilot had time to set range and maintain a steady track, the mathematics were unforgiving. For Japanese aviators already operating under increasingly desperate circumstances, shortages of fuel, inexperienced replacements, and overwhelming enemy numbers, this added sense of technological inferiority was deeply demoralizing. Post-war interviews would later reveal that many Japanese pilots regarded advanced American fire control systems as among the most psychologically damaging technologies they faced. It was not just the physical danger, but the realization that there were fewer and fewer ways for individual skill to compensate for the enemy's industrial and technological advantages. Behind every Mark 18 sight that found its way into a Corsair cockpit lay a complex network of factories, machine tools, and workers. The technical operation of the sight was impressive in its own right. A purely mechanical computer that performed real-time calculations without electronics. Yet building thousands of such devices for wartime service presented its own formidable challenge. The Mark 18 operated on the principle of conservation of angular momentum. Once powered, its gyroscope spun at high speed, maintaining their orientation in space even as the aircraft maneuvered. As the fighter pitched or yawed, the gyroscope housings rotated relative to the spinning rotors. Precision gears measured this relative motion and translated it into movement of the sight's internal mirrors, which in turn moved the illuminated reticle. The tolerances involved were minute, often measured in thousandths of an inch. Components had to fit together perfectly so the sight would respond smoothly to small changes in motion without sticking, binding, or drifting off calibration. The gyroscopes themselves were compact marvels, rotors balanced with extraordinary care, supported on bearings that had to function reliably under high G loads and abrupt maneuvering. At Sperry's production facilities, quality control procedures were rigorous. Each site underwent extensive testing on specialized stands that simulated aircraft maneuvers. Technicians verified that the computed deflection remained accurate across a range of turn rates and distances. Any site that failed to meet these standards was not simply discarded. It was returned for adjustment, remachining, or rebuilding until it met specifications. The challenge was not only to construct such instruments, but to do so at scale. Wartime demand required thousands of sites for aircraft operating in multiple theaters. To meet that need, Sperry adopted and refined mass production techniques tailored to precision instruments. Parts were designed for interchangeability, so that subcomponents produced in different plants could be assembled into a single site without extensive fitting. This modular approach paid dividends both in production and in the field. Maintenance personnel in forward areas could replace individual components instead of discarding an entire site. Spare parts were stocked at depots throughout the Pacific, allowing damaged or malfunctioning units to be repaired quickly. Integrating the Mark 18 into Corsair cockpits required its own careful work. Engineers had to place the sight where it was clearly visible, yet did not obscure the pilot's external view of the sky. Controls for setting range and wingspan needed to be easy to reach and manipulate without distracting from flying. The throttle-mounted twist grip for adjusting the ranging reticle was a direct answer to this requirement. The pilot could adjust the sight with the same hand he used to control engine power, reducing the need to take a hand away from essential controls. To refine the layout, engineers consulted experienced combat pilots who understood the practical demands of high-stress maneuvering. Their feedback influenced small but important details: angles of mounting brackets, placement of switches, and the brightness of illumination, until the sight became something pilots could operate almost instinctively. Training was the next essential piece. The Mark 18 was designed to simplify deflection shooting, but it was not magical. Pilots needed to understand what the moving reticle represented and how to interpret its behavior. Training programs emphasized practical comprehension over theoretical explanation. In ground school sessions, instructors taught the basic principles of gyroscopic deflection computation without drowning pilots in mathematics. They explained that the sight knew how fast the aircraft was turning because of the gyroscopes, and that it combined that information with the set range to place the reticle ahead of the target. What mattered to pilots was not the exact derivation of the formulas, but when and how to trust what the sight showed. In the air, training flights included practice intercepts against target aircraft. Pilots experienced firsthand how the reticle behaved as they tracked moving targets, how it stabilized after maneuvers, and how sensitive it was to smooth versus erratic flying. Instructors stressed that the sight worked best when tracking was steady. Wild, abrupt movements could momentarily confuse the gyroscopes, causing the reticle to lag until the system settled again. Pilots also learned the limitations of the system. After violent reversals, the gyroscopes needed a few seconds to re-stabilize. Firing during this period might not yield accurate results. Experienced pilots learned to time their attacks, initiating their firing runs once the sight had settled and the reticle's movement matched the target's motion in a predictable way. Even with these limitations, the Mark 18 represented a substantial leap forward. Pilots who had previously struggled with deflection shooting found themselves achieving consistent hits. The sight did not make air combat easy. It remained a deadly and complex business, but it removed one of the most technically demanding tasks from the pilot's mental workload. The overall record of Corsair operations during World War II provides the backdrop to evaluate the Mark 18's place in history. Navy and Marine Corsairs flew 64,051 operational sorties and achieved 2,140 air combat victories at the cost of 189 losses to enemy aircraft. This produced an overall kill ratio of about 11-1, marking the Corsair as one of the most successful fighters of the war. These numbers, however, represent combined performance across the entire conflict, encompassing aircraft equipped solely with reflector sights, as well as those upgraded with gyroscopic sights. The available declassified records do not provide a clean, statistical separation between kills achieved by each sight type. What does emerge clearly is the testimony of the pilots themselves. Men who flew with both reflector sights and the Mark 18 consistently reported that the gyroscopic sight made deflection shooting more reliable and less dependent on natural talent. Squadron reports, personal memoirs, and after-action analyses all point in the same direction. The Mark 18 improved the probability that a given burst of fire would result in hits. The Mark 18 did not, by itself, create the Corsair's formidable reputation. That reputation rested on a combination of attributes. The F4U's speed advantage allowed pilots to dictate when and where to fight. Its rugged airframe absorbed damage that would have destroyed lighter Japanese aircraft. Its heavy armament ensured that when bullets hit, they did devastating damage. The Mark 18 amplified these existing strengths. It made it easier for pilots, especially those with average initial skill, to exploit the Corsair's inherent advantages. It narrowed the performance gap between naturally gifted marksmen and those who needed mechanical assistance to perform the same complex tasks. As the war ended and the world moved into the jet age, the Mark 18 story continued in quieter form. Some Corsairs equipped with the sight remained in service and saw combat again during the Korean War from 1950 to 1953. Marine squadrons flying close air support and interdiction missions still relied on mechanical gun sights mounted in cockpits now decades old, even as new technologies began to emerge around them. These experiences had a lasting impact on Japan's post-war defense philosophy. When the Japan Self-Defense Forces were established in the 1950s, their approach to air power emphasized advanced avionics and weapons systems over pure maneuverability. Pilots who had once fought against Corsairs, equipped with Mark 18 sights, now recognized that future aerial combat would increasingly be decided by sensors, computers, and guided weapons rather than by the raw flying skill of individual pilots alone. The same technological progression unfolded elsewhere. The transformation of aerial gunnery from an art to a science, accelerated by the introduction of gyroscopic sights, reached its logical culmination with air-to-air missiles. By the 1950s, guided missiles began to appear in operational service, removing even the requirement that a pilot line up his guns with the target at all. Instead, the pilot's task shifted toward placing his aircraft in a position where the missile's systems, radar, infrared, or other, could acquire and track the enemy. In a span of less than 15 years, air combat moved from fixed reflector sights to mechanical gyro computers like the Mark 18, and then to missile systems with their own guidance. It was an extraordinary pace of change. By the time American pilots flew over Vietnam in the 1960s, the fundamental gyroscopic principles pioneered in the Mark 18 had been absorbed into more sophisticated fire control computers. These systems combined radar ranging, automatic deflection computation, ballistic corrections, and target identification into integrated packages that bore little outward resemblance to the mechanical boxes of 1944. Yet at their core, they still relied on measuring the motion of the platform, computing where a weapon needed to be pointed, and presenting that information to the pilot in a usable form. Within this broader arc, the Mark 18 occupies a transitional position. It bridged the gap between the era of instinctive gunnery and the age of guided weapons, between pilots like Kenneth Walsh calculating lead angles by eye and future generations relying on complex electronic systems. The personal stories of the pilots who flew with and without the Mark 18 illustrate that transition. Kenneth Walsh, who had first become a Corsair ace in 1943 using only a reflector sight and his own remarkable shooting ability, finished the war with 21 confirmed victories. For his actions on August 15, 1943, when he attacked a superior force of Japanese aircraft despite damage to his own Corsair, he received the Medal of Honor. Walsh remained in the Marine Corps after the war, eventually retiring with the rank of lieutenant colonel. His career spanned the movement from propeller-driven fighters armed with machine guns to more advanced aircraft carrying guided missiles. He had lived through the shift from instinctive, seat-of-the-pants gunnery to technology-assisted combat. Lieutenant Robert McClure followed a similar long arc of service. He survived the war with 7 confirmed victories and stayed in the Marine Corps until 1965, retiring as a colonel. In retirement, McClure wrote about the technological changes he had seen, from reflector sights to gyroscopic gun sights and beyond. He stressed that while the Mark 18 made deflection shooting more reliable, it did not make air combat safe. The sight removed one variable from a complex equation, but many others remained. Altitude, energy management, situational awareness, and tactical positioning still determined whether a pilot lived or died. An aviator with a perfect gun sight could still be bounced by an unseen enemy, outmaneuvered, or forced into a hopeless situation. The Mark 18 improved the odds, but it did not guarantee survival. The physical gun sights themselves followed a predictable path. Some continued in service on late-model Corsairs, particularly in the close air support role in Korea. Others were placed in storage or scrapped as aircraft were retired. A small number found their way into museums and private collections, where they remain today. Solid, metal artifacts from a time when mechanical computers represented the cutting edge of applied physics and engineering. Yet the true legacy of the Mark 18 lies less in the surviving devices than in the conceptual and industrial frameworks they embodied. The site's development required close cooperation between scientists, engineers, manufacturers, and combat pilots. Theoretical physics guided the design of gyroscopes and balancing systems. Manufacturing engineers solved the problem of producing them in quantity without losing precision. Pilots provided feedback from real combat, highlighting what worked and what needed improvement. This model of collaboration, linking laboratories, factories, and frontline units, became a template for later weapons programs. The Mark 18 also demonstrated the advantages of pragmatic procurement. Rather than insisting on inventing every technology from scratch, the United States adopted a proven British concept and adapted it for mass production. That willingness to integrate foreign innovations when they offered clear advantages would benefit American military aviation throughout the Cold War and beyond. The manufacturing techniques developed for Mark 18 production also had lasting effects. Modular assembly, interchangeable parts, and distributed production facilities became hallmarks of American industrial strength. The same principles applied later to radar systems, jet engines, and eventually electronic computers, forming an industrial base capable of producing complex systems at a scale unmatched by most other nations. The pilots who used the Mark 18 were among the first generation to operate in an environment where humans and automated systems worked together intimately in combat. They had to learn how to trust a machine without becoming dependent on it, how to exploit its capabilities without forgetting their own responsibilities. Their experience provides early examples of what is now often called human-machine teaming, a partnership that remains central in modern warfare and increasingly in civilian life as well. Assessing the Mark 18's exact impact on war outcomes is difficult. Official records confirm that it was produced in substantial numbers, installed in numerous Corsair and Hellcat squadrons in 1944 and 1945, and rated highly by pilots. After-action reports recorded shorter engagements, improved hit probabilities, and more efficient use of ammunition in units equipped with gyroscopic sights. What cannot be cleanly separated in available declassified data is the exact statistical portion of the Corsair's 11-to-1 kill ratio attributable specifically to the Mark 18, as opposed to factors like pilot experience, evolving tactics, or the declining quality of Japanese opposition late in the war. The historical record remains incomplete in that regard. What is clear is that the Mark 18 represented a meaningful advance in fire control technology. It worked reliably in combat, could be manufactured in large quantities, and could be learned by pilots without requiring years of specialized training. It was not glamorous, and it did not lend itself to dramatic headlines. But it solved a concrete problem: how to hit maneuvering targets during high-speed aerial combat with greater consistency. For Corsair pilots in 1945, the Mark 18 was not an abstract symbol of industrial power. It was a practical tool bolted into their cockpit, a tool that made a difficult job slightly more manageable. It could not eliminate danger, but it tilted the balance in their favor when seconds and inches determined life or death. In the broader history of aviation, the Mark 18 stands as a transitional technology, linking the age of mechanical aiming to the era of electronic computation and guided missiles. It taught machines to handle part of the aiming task, leaving humans to decide when and at whom to fire. The principle it embodied, that machines could perform certain calculations faster and more accurately than humans, would eventually spread into every corner of modern life. The story, often summarized as, "Japan never expected gyro gunsights to turn Corsair pilots into snipers," is, at its core, the story of technology meeting necessity. It is the story of British scientists confronting the limits of human aiming, of American engineers transforming that concept into a mass-produced instrument, of factory workers machining components to microscopic tolerances, of logisticians moving delicate sights across oceans, of mechanics installing and maintaining them under primitive conditions, and of pilots trusting that shifting reticle in the heat of combat. It is a story of systematic problem-solving rather than sudden miracles. The Mark 18 did not rewrite the war in a single stroke. It quietly, steadily improved the effectiveness of thousands of engagements. In doing so, it helped push aerial warfare along its path from individual artistry toward integrated technological systems, one spinning gyroscope at a time.